Okay. Okay. We are dealing with the module number 3, classification of the thermodynamics process properties. Three different properties are there: reference properties, energy properties, and derived properties. Okay. Reference properties, this we can call it as something like an absolute properties. Absolute properties. Okay. Then the primary properties such as the temperature, pressure, volume, this can be called as the reference properties. And if you see the energy properties, students, can you able to see the picture? Can you able to see the screen? Screen is visible. Hello? Hello, students?
Yes,
Screen is
sir.
visible to you? Huh? Okay. Yeah. The next comes the energy properties. 4 different energy properties are there: internal energy, enthalpy, Helmholtz free energy, and the Gibbs free energy. The internal energy is if you take any atom or molecule, the atomic or subatomic particles like electron, protons, and all, it will not be ideal. It will be moving here and there, and it will possess some rotational, translational, vibrational energies. Okay. Therefore, these energies, that is a function of temperature also. This energy is called internal energy. The internal energy can be measured with the help of temperature. If the object is at a higher temperature, it means. If it is at lower temperature, it means its internal energy will be low. The next comes the enthalpy. The enthalpy means the sum of the internal energy and the external work done. And therefore, E plus PVI we can call. The product of a pressure volume is also a form of energy, which we can call it as a work, okay, or the energy in transit. Okay. The next comes the Helmholtz free energy and the Gibbs free energy. Helmholtz free energy is the maximum work that can be performed by a system. It is called the Helmholtz free energy. Otherwise, it is called the work function. The next comes the Gibbs free energy. If you take a galvanic cell, in the galvanic cells, it will be doing some electrical work. Apart from this, there will be some expansion. Okay, expansion of the liquid. Expansion of the liquid, I mean expansion of the electrolyte, isn't it? Okay. Therefore, here in this case, the expansion of the electrolyte, which is also a form of energy, that is cannot be converted into useful work. Okay. Therefore, the electrical energy is the only useful energy which is available for the case of galvanic cell, isn't it? Okay. Therefore, in this case, the useful work for the case of a galvanic cell is the Gibbs free energy. It is a form of a chemical energy. That's all. Okay. Therefore, these are the 4 different types of the energy properties. The next comes the derived properties. Okay. What do you mean by derived property? Derived property mean the properties which are the property which can be predicted with the help of the fundamental properties or energy properties. Okay. Therefore, that is called a derived properties. Okay. For example, for the derived properties of a specific heat, coefficient of expansion. The expansion means thermal expansion. If you take a material, and it may be a solid or it may be a metal or something else. Therefore, what will happen when you heat that object? It will try to expand. Okay, that is called the coefficient of expansion, which is represented as a beta. Joule-Thomson coefficient. We have studied about the Joule-Thomson coefficient. The positive. What is the meaning of a Joule-Thomson coefficient? Change in temperature with the change in pressure at the constant enthalpy. Isn't okay? Therefore, this can be written as a del T divided by. See, all of you just listen here. Del T divided by del T divided by del P at the constant enthalpy. This is nothing but the Joule-Thomson coefficient. Okay. Therefore, this is a derived property. This is derived for the fundamental property like a temperature, pressure. Isn't okay? Then this is called a since it is derived from the fundamental properties, Joule-Thomson coefficient can be called as a derived property. Okay. Apart from this, we have the coefficient of the compressibility also. Coefficient of compressibility mean change in volume to the original volume. Okay, at constant pressure we can take change in volume to the original volume at the constant pressure. Okay, therefore this is called a compressibility coefficient. Okay, therefore, okay, so many derived properties are there. Okay, therefore these are the different properties. Okay, next our objective is we want to find a relation between these properties. That is the reference properties, energy properties, and derived properties. We want to get a relation because some property can be measured, especially the reference properties can be measured with the help of any measuring instruments like a temperature, pressure gauge, or something like that. Okay, but the remaining properties, which cannot be measured, and there should be a relation. We need a relation between the reference properties and energy properties and the derived properties. Then only it can be predicted, or it can be judged, or it can be calculated. Okay. Therefore, further to know, our next objective is we want to derive the Maxwell thermodynamic relation. Okay. Therefore, before entering into the Maxwell thermodynamic relation, we want to know what is the mathematical form of a Helmholtz free energy. The Helmholtz free energy is represented as A, which is equal to U minus Ts. U is the internal energy, Ts the product of T and S is nothing but the Q. Q is the heat supplied. Okay. Therefore, this is the Helmholtz free energy, the definition for the Helmholtz free energy in the mathematical form. Okay. Similarly, we know the physical significance we have seen is nothing but the work function. How much work is done by the system? Okay. The next, Gibbs free energy. For the case of the Gibbs free energy, the mathematical expression for the Gibbs free energy is G is equal to H minus Ts, where H is the enthalpy, and Ts again is the heat supplied to the system or heat absorbed by the system, like that. Okay. Then with this, we are going to derive the relation between the various properties. Okay. Then the first one, the fundamental property relation. The fundamental property relation was obtained from first law of thermodynamics. We know the first law of thermodynamics. Okay, whatever the heat supplied, a part of the heat will be used for doing the work, and the remaining the part will be used for increasing the internal energy of the system. Okay. Therefore, that's what given. Okay, this is the first law of thermodynamics. Equation 1 is nothing but the first law of thermodynamics. Okay, good. Then the dq can be expressed using the second law of thermodynamics. Okay, just listen here. This one, the dq can be expressed with the help of the second law of thermodynamics, T into ds. dq is equal to T into ds. Therefore, I am going to replace this dq in the equation 1 with the T into ds, which is from second law of thermodynamics, and ultimately I got the expression like this: du, that is the change in internal energy, is equal to T into ds minus P into dv. I can write. This is the combined form of the first and second law of thermodynamics. That's all. Okay. The next, what we are trying to do, this is for the case of a H is equal to PV. That means all the energy properties, from my energy properties, I am trying to translate to some with the help of first and second law. I am trying to express du is equal to T into ds minus P into dv. That is from the first and second law combined form of first and second law. Using the same principle, I am going to express the H is equal to U plus PV. Also, I am going to express. Okay, the U can be replaced with T into ds minus P into dv. That's all. Plus, and the PV is there. Okay, therefore, what I can do, this PV, I can I can differentiate. That means, while differentiating P, first you have to keep the P constant and differentiate with respect to V, then V constant and differentiate with respect to P. Okay, therefore ultimately I got the expression like this: dH equal to du plus P into dV plus V into dP. That is the equation number 3 I got. Okay, therefore equation number 2 and equation number 3 are important now. These two are important. Okay, pressure I can measure, internal energy I can measure, okay, volume I can measure. Okay, the next, the Gibbs free energy and the Helmholtz free energy I am going to express. What is the Gibbs free energy and the Helmholtz free energy? Okay, Wait, all of you wait. See here. Okay. Then here, the definition from the Gibbs Helmholtz free energy is A is equal to U minus T into S. Isn't? We have to differentiate. Okay, after differentiation of this equation, see all of you just listen here. I am differentiating this equation. This equation can be called as a 3b. Let it be 3b. I want to differentiate the equation 3b. After differentiation, I'll be getting dA is equal to du minus T into ds minus s into dt. That's all. Already, I know the expression for du from the previous. What is the du here? Must you wait. Here the du, P into ds minus P into dv. Isn't it? Okay, the equation number 2. By using the equation number 2, okay, I am going to substitute in equation number 4. And ultimately, I got the expression du is equal to, that is the this one equation. Okay, see here the equation number 4 I got like du minus T into ds, substitute. And ultimately, I got the expression dA is equal to minus P into dV minus S into dt. Okay. Similarly, I have to get the expression for dG. G is the Helmholtz free energy. Okay. Then, all of you listen here. This one is the Helmholtz free energy. How I am obtaining for the case of the Helmholtz free energy. For the Helmholtz free energy, it is written as G is equal to H minus Tus. This is from the definition of the Helmholtz free energy. Definition of the Helmholtz free energy. Okay. Therefore, you know, G is equal to H minus Ts and dG is equal to something dH minus T into ds minus S into dt. That's all. Okay. Substitute and ultimately I got the expression. Okay. Now I have 4 different equations for 4 different energy properties. E, H, A, G. That's all. Okay. Then this one, there's 4 different equations. You know, that is. Wait. Okay. The 4 different energy equations I do have now. Okay. Then from these 4 different energy equations, I'm talking about the energy equation. D is equal to T into ds. All of you wait. All of you just listen here. Okay. Then this is the first equation I got, isn't it? This equation, all of you just listen here. This is the first energy equation that is expressed in terms of a temperature entropy like this. Okay. Therefore, from this, what I can say, the U is a function of S comma B. U is a function of U. U are internal energy, I can write. The internal energy U is a function of S comma B, I can write. It is a function. Okay. Therefore, that means, you know, I know that U is a state function. State function means what? U, if you, okay, you see here, U is a function of 2 different variables, S and V. Okay. Then this U can be differentiated by 2 ways. One is differentiating U or internal energy with respect to volume first, then entropy second. This is one way. The second way, differentiating U with respect to S, that is entropy first, then the by keeping volume constant. Okay, this is the second method. Okay, but if you follow two different paths, you know, the second differential will be the same. That means why it is the same? Because U is a state function. U is a state function. Okay. Now, what I'm going to do, from the equation 2, I have taken the equation 2. Okay. Then the equation 2 for the case of a constant volume process. What do you mean by constant volume process? For the case of a constant volume process, the meaning is dV will become 0. dV will become 0. Therefore, the equation 2 for the case of this equation, the equation 2 for the case of a constant volume reaction or constant the reaction constant volume process. Okay, this will reduce us to the form dou U by dou S at the constant V, which is equal to T. Equation number 3. Okay, then the same equation number 2 for isentropic process. Isentropic process means ds is equal to 0. Okay, for the isentropic process, when ds is equal to 0, the equation 2 reduces to dou U by dou V at constant here, that is equal to minus P. That's all. Now, what I have to do, I have the third equation, I have to differentiate with respect to V, the third equation. I have a third equation, isn't it? All of you just listen here. I have a third equation, this equation. How I got this equation? From 2 only I got the equation. How? By putting dv is equal to 0. dv is equal to 0 is applicable for constant volume process. Okay, by selecting a constant volume process, in the equation 2, P into dv will become 0. Then the equation 2 reduces to the equation 3. Dou U by dou S at the constant V. Okay, constant V means, the meaning of constant V is, see here, the V is kept outside the bracket, isn't it? If it is so, the meaning is that variable which is present outside the bracket, that is kept constant. That is the meaning. Okay. Therefore, the equation number 3, it is a change in internal energy when there is a change in entropy at constant volume. That is the meaning of equation number 3. Okay. Similarly, I got equation number 4. The meaning for equation number 4 is change in internal energy when there is a change in volume at constant entropy. That is the meaning, which is nothing but minus P, the decrease in P, that's all. Okay, now what I have to do, I have to differentiate both the equation 3 and 4 with respect to the next variable, the other variable. See here, I have to differentiate equation 3 with respect to, I have to differentiate this equation number 3 with respect to V now by keeping S a constant. Okay. Therefore, I got this one. Okay, I got the equation number 3. From the equation number 3 only, I got the equation number 5. I differentiated U with respect to V now by keeping S constant. Okay, I got the equation, but both the sides we have to differentiate. Therefore, the right side, I got the expression dou T by dou V at a constant S, which is something but the equation number 5. Okay, now you have to go for the equation number 4. The same equation, what you have to do in equation number 4, I am telling. Okay, this I have to differentiate both the sides. Both the sides I have to differentiate with respect to S by keeping V constant. Okay. By doing so, I got the equation number 6. I got this is the equation which I got. Dou square U divided by dou S dou V is equal to minus dou S by dou P by dou S at constant volume. I got this expression. Okay. Since U is a state function, How do I know that U is a state function? Because the internal energy depends only from the physical observation. The internal energy depends only on the end and the final state, not on the path it followed. Okay. Therefore, it is independent of the path followed. Okay. Therefore, what I can write, this is okay. Therefore, since U is the state function, I can write like this. All of you just listen here. I can write this one. Okay, that is dou square U divided by dou S dou V is equal to dou square U divided by dou V dou S. Okay, this condition is applicable only for state function. This condition is not applicable for the case of a path function. It is not applicable. It's not applicable, not at all applicable. If U is a path function, then definitely the second differential, dou square U divided by dou S dou V, will not be equal to dou square U divided by dou V dou S. That's all. Now, from the equation 5 and 6, I have time going to the next this one. Okay, see here. Okay, by equating this one, that is both the right side of the second differential equation, I got the ultimate relation like this. See here, Why I am equating like this? Why I am equating like this? Because U is a state function. If U is a state function, though it followed two different paths, the ultimate result or ultimate state will be the same. This is applicable only for the state function, not for the path function. Okay. Therefore, this is applicable for all the state functions. What are the other state functions that we know? Apart from this, U is one of the energy property. Other energy properties are H is also an energy property. Then A is energy property and G is also an energy property. Therefore, this condition, this is applicable for both internal energy, enthalpy, Gibbs free energy, and Helmholtz free energy. Okay. By equating this one, ultimately I got this expression dou T by dou D at the constant S equal to something. Okay. See here, I got this expression. Okay. Now, in this expression, check what are the properties that I can measure. Temperature I can measure, volume I can measure, pressure I can measure. If I can measure all the three, then I can calculate what is the change in entropy. What is the change in entropy? All of you can able to understand. Okay. Therefore, this is the application of this studying about the energy properties. Application of this energy property. Okay. Therefore, this equation is called Maxwell's thermodynamic relation 1. Maxwell's thermodynamic relation 1. Okay. The next question is, this is based on internal energy. We derived it based on internal energy. Similarly, we can get the Maxwell thermodynamic relation 2 starting from the enthalpy H. And starting from A, Helmholtz free energy, we can get the Maxwell thermodynamic relation 3. Okay. Then by using this G, we can find out what is the Maxwell thermodynamic relation 4. Okay. Therefore, our objective is we want to find a relation between the properties which can be measured directly and the properties which cannot be measured directly with the help of these relations. That is the objective. Okay. Therefore, this is Maxwell's first equation. Okay. The next Maxwell's second equation. Okay. All of you just listen here. Similar way, it will be very easy to do. Okay. Okay. Let's see here, all of you. I have taken the second energy property. Previously, I have started with the first energy property, internal energy. Here, we are going to start with the second energy property called enthalpy. This is the enthalpy. Okay. What is the definition for the enthalpy? Enthalpy is equal to it is a sum of internal energy plus pressure volume work. Internal energy plus pressure volume work. Okay, put together is called enthalpy. Okay, that's all. We will start from the internal. This internal energy can be replaced with the U. The U and the E both are same only. All of you just listen here. This E and the U both are same. Some book they will be using capital U as the internal energy. Some they will use capital E. Okay. Therefore, I can write like this. Okay. The equation 1 I am going to differentiate. Equation 1. All of you just listen here. Equation 1 I am going to differentiate. Okay. Okay. Then by differentiating this equation, I got this equation that is dH plus dA is equal to du plus P into dV plus V into dP. That's all. Ultimately I got this expression like this. Okay. Then from the first and second law of thermodynamics, I have to replace. Okay. Then after replacing this one, ultimately I got this equation dH is equal to something. Okay, dH is equal to T into ds plus V into dP. Okay. All of you can understand. It's very simple only. If you write once, then it will be very easy that all the totally four relations are there. Maxwell's thermodynamic relations, so 4 different relations are there. All will be very easy to derive. Then I think it will come as a big question. If you I don't know what is the mode of third internal. If the third internal is like a return test, then it may be asked as the big question. Okay. then dH is equal to T into ds plus V into dP. Okay, that is the ultimate equation I got starting from H is equal to E plus PD. That's all. Okay, now I want to state the conditions now. Here in the right side, two different variables or two different terms are there. This is the first term and this is the second term, isn't it? Okay. I want to remove this term. Is it, if it is so, then what condition I have to take? I have to take constant pressure. Otherwise we will take this one. I want to remove this term. That means this term will become 0 when d is equal to 0. d is 0 means ds is nothing but a change in entropy. If the change in entropy is 0, then what is the meaning of that one? Constant entropy process. Otherwise, we can say isentropic process. Okay. For isentropic process, this ds will become 0. Then the equation 4 will become dH equal to V into dP. That's all. Otherwise, I can write like this. This dP, I can bring it down and I can write like this. dH divided by, dou H divided by dou P at a constant dH, that is equal to V, I can write. Okay. Similarly, the same equation number 4 only, but for constant pressure process, equation number 4 will reduce to no. Okay, what I did, okay, we leave it this one. Wait. Okay, up to equation number 5 is correct only, no problem. Up to equation number it is correct. Okay, the next step, what I am going to do, I am going to differentiate the equation number 5 with respect to entropy by keeping the pressure constant. By keeping the pressure constant. Okay, I got this equation. Okay, but what about the H? H is here state function. That means, okay, if you look at the term which is present in the left side, you know, first this H is differentiated with respect to P and then S. Sorry, S first, then P. Okay, then if you differentiate the H first with respect to P, then S, you know, then it is not going to change because H is a state function. Okay, then you will go to see here. The same equation for the isobaric, the equation number 4 for the isobaric. Isobaric means pressure should be equal to 0, the change in pressure. That means dP is equal to 0. When you select dP is equal to 0 from the equation 4, then ultimately we got the equation number 7. This equation we will get. Okay, dou H divided by dou S at constant pressure is equal to T. Okay, that's all. This is what I am going to do. I am going to differentiate the equation number 7 with respect to P by keeping S constant. By keeping S constant. Ultimately, I got the equation number 8. Okay. Then comparing equation number 6 and 8. Okay. Dou square H divided by dou P by dou S is equal to this thing. Okay. This condition, you know, I'll have to just listen. This condition, you know, this is applicable when H is a state function. We know that H is a state function. Okay, therefore, you know, if left side is equal, then right side should also be equal. The right side is nothing but dou V by dou S at constant pressure is equal to dou T by dou T by dou P at constant entropy. Therefore, in that I can measure what is V, or change in volume, change in temperature, change in pressure I can measure. But I cannot measure this change in entropy. Therefore, from this I can predict what is the change in entropy when there is a change in volume under constant of pressure. Okay, then this can be easily predicted with the help of equation number 2. This is the Maxwell's equation. Okay, the second Maxwell equation. Similarly, we have to start from the Helmholtz free energy and the Gibbs free energy. That's all. Okay, therefore, by using Helmholtz free energy, I got this ultimate equation like this. Dou S divided by dou T, equation number 3, which is in the Roman letter. Okay, see this one. Okay, this is from the A is the Gibbs free energy, not Gibbs. Helmholtz free energy. Dou S by dou V at constant temperature is equal to dou P by dou T at constant temperature. That's all. Okay. Similarly, we can proceed with the Maxwell's equation for the case of Gibbs free energy. The definition for the Gibbs energy we have to take. This is the definition for the Gibbs free energy. We have to start from here, and with the help of first and second law of thermodynamics, we have to replace this HA, and ultimately we got this expression like this. The number 4, we got the equation number 4 like this: d is equal to t into ds minus p into dv. Then we have to rearrange, and ultimately we got the expression like this, equation number 6. Okay. Then we want to make, okay, here in equation number 6, two terms are there in the right side. One term I have to choose, and remember, and the next term I have to make it 0 by selecting suitable condition. If I want to make this the p is equal to 0, this p is equal to 0, I have to select a constant pressure process. Next time I have to take a dt is equal to 0. That means changing temperature is equal to 0, which is nothing but isothermal process. That's all. And after selecting all these things, we will be getting this expression, and we have to differentiate twice. And ultimately, I got the expression like this. And let me just listen here. Ultimately, I got the expression. Okay. See here, minus dou s by dou p at constant temperature is equal to dou v by dou t at a constant pressure, which is nothing but the fourth Maxwell thermodynamic relation. So, okay, these are the 4 different Maxwell thermodynamic relations. It will be very easy. The only principle is, what is the definition of all energy properties? E means what? Okay, now what is it? dq is equal to de minus t into ds. Okay. Okay, we have to start from the 4 most fundamental energy properties. Okay, H, E, A, G. We have to start. Okay, and by using first and second law of thermodynamics, we have to get the relation. Okay, then after that we have to select a suitable condition to make any one of the compound, or sorry, any one of the differential should be equal to 0. Okay, then after that, we have to differentiate twice with the different roots. Okay, different root means what? Pressure first, volume second. That is one root. Volume first is pressure second. That is another root. Okay, like this. And ultimately, we have to get what is the Maxwell thermodynamic relation. That's all. Okay. It will be very okay. Therefore, this is the overall view of the Maxwell thermodynamic relation. Okay. Therefore, this is the first relation, which is appended from E is equal to T into E is equal to this one. Okay. Then the second one is H is equal to what? H is equal to E plus PD. E plus PV. Okay. The third one is A is equal to E minus TS. Okay. The fourth is G is equal to H plus TS. H plus TS, like this. Okay. Therefore, we have to derive all these things. Okay. These are called the Maxwell's thermodynamic relations. That's all. Okay. This is the mnemonic form. Okay. That is a short form. How to use. Next class, we will see the Clapeyron equation. Students, all of you give your attendance. Number one. Number one, absent. Number two,
Present, sir.
number three,
Present,
number
sir.
three, four,
Present, sir.
8,
Present, sir.
9,
Present, sir.
10,
Present, sir.
11,
Present, sir.
12,
Present, sir.
13, number 13, absent.
Sir, in the chat box.
Number 14,
Present, sir.
15,
Present, sir.
17,
Present, sir.
18,
Present, sir.
19,
Present, sir.
20,
Present, sir.
21,
Present, sir.
22,
Sir.
okay, 23,
Present, sir.
24,
Present, sir.
25,
Chat box.
20, okay, 26,
Present, sir.
27,
Present, sir.
28,
Present, sir.
29,
Present, sir.
30,
Present, sir.
31,
Present, sir.
32,
Present, sir.
34, 34, Shivani, 35, 35,
Chat box.
36,
Sir,
36,
Chapo.
37,
Present, sir.
38,
Present, sir.
39,
Present, sir.
40,
Chat box.
45,
Present, sir.
47,
Present, sir.
49,
Present, sir.
54, 54, Blessy, absent. 57,
Sir, in chat box.
2, 57,
Yes, sir.
68,
Present, sir.
72,
Present, sir.
74,
Present, sir.
76, 76,
Present, sir.
okay, 88,
Present, sir.
okay, today's absentees are 1, 34, 54, okay.
Sir, 34 present.
What you were
Sir, one
doing?
present, sir.
One I asked so many times, you did not respond. One and
54 is also present, sir.
54. Sherwan, today there is no absentees. Okay, you can leave. Thank you. Okay, thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir. Have a good day.
Thank you. Thank you. Thank you.